we will be beginning with the model of the transmission line with some losses included in the transmission line in the series and in the parallel path. Okay. So, I will start with the equivalent circuit for the unit cell of the transmission line. Okay. So, I have a series inductor just as we had seen in the prior classes, okay, and we add a resistor in the series path. Okay. In the prior lectures, in the lossless transmission line, we had connected a parallel capacitor in the model. Assuming that there is a conductive path across the capacitor, a conductor is added in the parallel path also. So, let the inductor be L delta Z, where delta Z is the space step or the dimension of the transmission line unit cell. So, this dimension is going to be Z. The position coordinate on the left hand side can be Z, and the position coordinate on the right hand side can be Z plus delta Z, right. And the series resistor is denoted by small r times delta Z. The unit of small r will be in ohms per meter. The parallel capacitor, as we had seen earlier, is C times delta Z. And to make the calculations simpler, instead of considering the parallel arm resistor, we consider this to be a conductor, so that we can add and subtract, we can add the impedances in the parallel arm when we are applying some circuit laws. So, the conductance is given by G delta Z. G is in mho or Siemens per meter. R is in ohm per meter. The voltage on the input side is denoted by voltage at position Z. The voltage on the right hand side is denoted by voltage at position Z plus delta Z. The current entering this section on the left hand side is marked by I of Z, and the current exiting this section is going to be I of Z plus delta Z. Okay. So, now this becomes the model of the transmission line with non-idealities included for the inductor and the capacitor. So, there is a series resistance for the inductor and a parallel conductance for the capacitor, right. And we can begin by applying the circuit laws that we have seen before. We can start by applying Kirchhoff's voltage law around the loop. Okay. So, we can start with the voltage on the left side, V of Z. Okay. And to be more precise from the previous lectures, now we can start to include position and time just to denote the level of complexity that we are going to be having, right. So, it is going to be V of Z comma t, right, and then we are having a drop on the inductor, a drop on the resistor, and those can be denoted. For example, the drop across the inductor is given by minus L delta Z dou I dou t, and if you want to be precise, you can say that this is at position Z minus the drop across the resistor R delta Z times I, and to be precise, we can say that this is at position Z at time t, okay, minus the voltage at the output of this transmission line section. So, we can mark this as V of Z plus delta Z comma t should be equal to 0. Okay. Now, the KVL has been written with both the space and the time included, right. As the limit delta z tends to 0, many things will get simplified, but these small details will be important when you write the program, right. You will need to know which quantity is at which spatial or temporal position. However, for now we are interested in finding out the relationship between output current and input current, output voltage with respect to input voltage. So, we can do a rearrangement of this equation. So, we can say that V of z plus delta z comma t, right, minus V of z comma t is equal to minus R delta z I of z comma t minus L delta z dou I dou t at position z. Okay. Now, bringing the delta z from the right side to the denominator, okay, we will be having V of z plus delta z comma t minus V of z comma t divided by delta z is equal to minus R I of z comma t minus L dou I dou t. Now, we can apply the limit delta z tending to 0, means that there is an extremely small section of the transmission line with the equivalent circuit that we have drawn. In that case, the left hand side becomes a spatial derivative of voltage. So, we will have dou V by dou Z is equal to minus R I minus L dou I dou t. Okay. Now, this will be the first telegrapher's equation. We notice immediately that the form of the equation remains almost the same. So, previously we had dou V by dou Z is equal to minus L dou I dou t, but now due to the inclusion of the series resistor, an additional term has popped into the first telegrapher's equation of minus R times I. Okay. The same way we can apply KCL for the incoming and outgoing currents in the section. If the incoming current is considered as positive and the currents that are leaving this transmission line section are considered to be negative, we can start with I of z comma t, which is the current that is entering the transmission line, okay, minus so the current that enters the transmission line is given by I of z comma t, and then we have a current that is branching and going through the capacitor arm and a current that is going through the conductor's arm. So, we will have two additional terms. Okay. So, we can write this down as C delta Z dou V dou t, and we can also be a little bit more precise about the position. We can say that it could be at Z plus delta Z. It is simply because of the way we have drawn the equivalent circuit, right. Simply because of the way we have drawn the equivalent circuit, we have drawn the capacitor and the conductor to be on the right hand side. So, we assume that this position is close to Z plus delta Z, right. Okay. C delta Z dou V dou t minus the current that is going through the conductor. So, that will be G V of Z plus delta Z comma t. Okay. So, since the unit of G is in mho or Siemens per meter, right. So, we are writing this as G times voltage, and I am missing a delta Z term, G delta Z V of Z plus delta Z comma t. And then there is a current that is leaving the transmission line section and going to the next section. So, that is denoted by I z plus delta z t is equal to 0. So, this will be the KCL for the currents that are coming into the transmission line section and leaving the section. We can rearrange this KCL to be I of z plus delta z comma t minus I of z comma t divided by delta z is equal to minus G V z plus delta z comma t minus C dou V dou t at z plus delta z. One could now take the limit where the transmission line section is really small, right. So, you can go ahead and apply delta z tending to 0. This will mean that the left hand side will become a spatial derivative of the current dou I by dou z is equal to minus G V minus C dou V dou t. Now, this becomes the second telegrapher's equation. One has to notice that in both these cases, there are some small details that one will have to consider while doing the programming part. For example, when you are taking minus G V, you are going to be having some different spatial or different time coordinates. If you are taking dou V by dou t, spatial coordinate is present z plus delta z, but the way you take the derivative, if you take V at t plus 1 and V of t and then you divide it by delta t, then that derivative will exist at V of t plus delta t divided by 2. So, there can be a detailed analysis on which spatial location and which temporal location each of these quantities exist, and one could then make a decision during the programming as to how to properly code it, right. I will not go into all the details, okay, because it is again taught in a higher level course in detail, but when we are going to be doing the coding in the next class, you will notice that tiny details will start to matter. If you take the equation as such, add or subtract quantities with your existing telegrapher's equation, you may end up with some errors. So, some changes in the way it is being programmed will be based on how these terms are existing in space and time, but I leave that exercise to you. Okay. So, now we have the two telegraphers equation. Right. We can now write these two equations also in the frequency domain, right. So, we can say that for periodic so we can say that if the transmission line is excited by a sinusoidal signal, for the lossless case we have already seen how to denote this. So, we could write down the two telegraphers equations to look like dou V by dou Z. On the right hand side, you will end up having minus R plus j omega L times I, okay, where I is given by say I e to the j omega t. Okay. So, the derivative on the right hand side will have R plus j omega L term coming into the picture, and the second telegrapher's equation will become dou I by dou Z equal to minus G plus j omega c times V. This is very similar to the lossless case that we have seen in the prior class. Okay. And we also know that when we have these kind of coupled partial differential equation, we can always create the wave equation from these two equations by decoupling them, right. So, this process we have done twice now. So, now I am going to directly go ahead and write the decoupled wave equation for the voltage. So, dou square V by dou Z square is going to be equal to R plus j omega L times G plus j omega c times the voltage. Here the assumption is that it is a sinusoidal excitation. So, we can represent this as V e to the j omega t, right. If this is the case and this is the wave equation, in order to write down the general solution, we can assume the right hand side to be composed of a quantity. So, we will define a new quantity. So, if gamma is going to be equal to square root of r plus j omega L times G plus j omega c, then the wave equation can be written as dou square V by dou Z square is equal to gamma square V. Okay. The first thing that we notice compared to our prior classes is that in the prior class for the sinusoidal excitation for the lossless transmission line, we had dou square V by dou Z square is equal to beta square V, where beta was not a complex number, right. But now we are having a complex number, right. Okay. We are having a complex number, it has a real part and an imaginary part, right. It has a real and an imaginary part. So, gamma is known as a propagation constant, and to be precise, it is a complex propagation constant. Okay. It is composed of a real and an imaginary part, and to denote that we write it in the form of a complex number alpha plus j beta. Okay. So, the propagation constant is written as alpha plus j beta, okay, where alpha is known as attenuation constant and beta, from our prior lectures we already know that this is going to be phase constant. Okay. So, the complex propagation constant is composed of an attenuation constant which forms the real part and a phase constant in the imaginary part. The unit of beta is going to be radians per meter. The unit of alpha is Nepers per meter, and the meaning of this has to be understood in some slight detail. It is in Nepers per meter, okay, and the propagation constant, the unit is simply per meter. Okay. If the wave equation is written as dou square V by dou Z square is equal to gamma square V, we already know how to write the general solution for this wave equation. We can write down the solution for the voltage, in this case is going to look like some V plus e to the minus gamma Z plus V minus e to the plus gamma Z. We have already discussed in detail about some forward wave and backward wave. The first term denotes the forward wave with a complex propagation constant gamma. The second term denotes the backward wave denoting with the complex propagation constant gamma again. So, the sign change here is just indicating that the first term is forward, the second term is a backward wave. Okay. So, the general solution is V plus e to the minus gamma Z plus V minus e to the plus gamma Z. Now, we can look at only the forward part and then try to see what the meaning of this alpha could be. Okay. So, taking only the forward part, okay, okay. Taking only the forward part, we can substitute for gamma to be alpha plus j beta. Okay. So, we can write down this forward part as V plus e to the minus alpha plus j beta times z. This becomes V plus e to the minus j beta z multiplied with e to the minus alpha z. Okay. Now, we notice that the first term in the brackets is similar to the term that we had for the lossless transmission line, where the model did not include the series resistance and the parallel conductance. Okay. So, it is V plus e to the minus j beta z. Because of the inclusion of two resistors, one in series with the inductor, one in parallel with your capacitor, we are having an additional term coming into the general solution for the forward wave. So, it is having an exponential minus alpha z. So, the exponent here is not a complex number, it is not a imaginary number, all right. So, this means that there are some details that we have to understand with respect to this, all right. First of all, we will write down that if alpha is equal to 0, we call this as a lossless transmission line, which is the case that we have seen in prior classes. The solution then becomes identical to what we had before. The second term outside of the bracket becomes equal to 1, all right. It is exponent of 0, so it becomes 1, and your general solution turns to the solution that we had in the prior classes. This is known as lossless transmission line. Okay. Now, if alpha is greater than 0, then we have to notice that alpha is going to be a positive number. If it is going to be a positive number, as z increases, there is going to be an exponential decay of the voltage term that is present in the square bracket. So, this term dictates what the magnitude of your voltage wave or the amplitude of your voltage wave will be, and it denotes that as the wave travels forward, this is a forward traveling wave, as it goes forward, it is going to decay exponentially in amplitude, right. So, if alpha is greater than 0, we just call this as a lossy transmission line. Okay. Diagrammatically speaking, previously when we had done the simulations, say for example, we had the position z coordinate in our simulations like this, and then we would be having some value of voltage which is coming into your transmission line due to the excitation. So, you will be having something like okay. So, the peak of your voltage will decay exponentially. That is what this e to the minus alpha z means. Okay. If your propagation constant is consisting of a real and an imaginary part, the real part will contribute to the loss, right, and the voltage will continuously decay, okay, and the imaginary part will just dictate the phase, and this part we are already aware of. Okay. The question then becomes, what if alpha is less than 0? Okay. If alpha is less than 0, then it is obvious that from the solution, as the wave travels forward, the amplitude will keep on increasing. Okay. Now, if the amplitude keeps on increasing, there has to be some physical interpretation for what is happening in the circuit diagram. The only way you can interpret that is you are supplying some external power, and that power is being converted into amplification of your existing voltage wave. In other words, it acts like a gain circuit of some kind if alpha is less than 0. So, if alpha is less than 0, you will have a transmission line with gain, but we can be sure that in our model that is not going to happen, because we have used only passive elements. We have used only resistor, inductor and capacitor. None of them are active elements which can provide amplification. So, if you did want to have alpha less than 0, the equivalent circuit diagram has to change. It has to include external power and use some kind of an amplifier. An example could be that if you use some operational amplifier of some kind somewhere, maybe you are boosting the voltage, and then you could have a change in your circuit. Optically, it means that you have a gain medium which will increase the amplitude of these signals. But alpha less than 0 is not under the purview of this course as of now, right. So, alpha is strictly positive for most of the cases that we are going to be dealing with, and that corresponds to a lossy transmission line. Okay. So, just to be very clear, the forward wave is given by say V plus e to the minus gamma z. You can write this down as V plus e to the minus alpha z times e to the minus j beta z. Okay. So, this term governs the amplitude, and this term governs the phase. Okay. And the unit of alpha is in nepers per meter, and I think we have to understand that unit a little bit more, so that we are comfortable with problems that we will be solving. So, if alpha is equal to say 1 nepper per meter, so the short form we will use is NP per meter. Okay. If alpha is equal to 1 nepper per meter, then what we are trying to say is the amplitude of the wave drops to 1 over E, okay, over a distance of 1 meter. This is the meaning of alpha, which is 1 nepper per meter. So, as your wave travels forward, if alpha for your transmission line is 1 nepper per meter, if the voltage wave travels 1 meter, its amplitude would have reduced to 1 over E of its input voltage amplitude. That is the meaning of 1 nepper per meter. Okay. So, this also means that we will have to quantify certain other terms in our transmission line which we did not worry about before. It means that practically many transmission lines are going to be having some value of resistor in the series, some value of conductance in the parallel path, which means that many of the transmission lines will be having some small amount of alpha, and it is going to lead to some exponential decay of the voltage as the wave is traveling forward, which means that there is some limit on the length of the transmission line that one can use to have a voltage wave traveling from one side and also be able to receive it on the other side. Okay. If you have a very long transmission line that is lossy, it is given that on the other side you are not going to be having a signal at all. So, this means that some new parameter has to be decided compared to before, all right, and one of these parameters is propagation length. Okay. Prior to this lecture, where we had not included resistance and the conductance, we had not worried about propagation length. We knew that the voltage wave that is launched on one side is going to reach the other side with a delay, and depending on the boundary condition there is going to be some reflection, etc. But now you are going to be worrying about what could be the length of the transmission line. So, objectively it is defined as the distance over which the amplitude drops to 1 over E its original value. Okay. So, the propagation length is defined as the distance over which the amplitude drops to 1 over E its original value. Okay. In short, propagation length L is given by 1 over alpha, and the unit obviously is becoming meter, even though alpha is in nepers per meter. One has to understand that the unit of the propagation length will become in meters, and the propagation constant, the unit is per meter. Okay. So, the propagation length is 1 over alpha. So, this means that if you did have a line of 1 meter and 1 nepper per meter is your alpha, that is actually its propagation length itself. Okay. So, the other things that we have to consider is the propagation length is signifying the length of the transmission line where the voltage or the amplitude will drop to 1 over E, does not mean it drops to 0. Okay. So, there can be some small value of the voltage wave traveling beyond this, right. But for practical purposes, we do not consider that to be a transmitted signal. We just say that the voltage wave has decayed significantly, but it does not mean that there is no voltage wave existing after this propagation length. If your transmission line is longer than the propagation length, it means that you are having very negligible amounts of signals, but does not mean you have 0 signal. Okay. Another way of looking at this problem is people usually launch an input power and they actually try to measure the output power at the end of the transmission line. Okay. So, if your input power so I call it as P in, okay, and the unit will be in watts, okay, and if the output power is going to be P out, right, in watts, right. In order to understand what fraction of your input power is coming at the output, one could simply take a ratio of P out to P in, all right. You will know what proportion of your input power is coming out. Since we are considering a transmission line with no active components, your output power is going to be always less than equal to your input power, and since we know that most of the conventional transmission lines will have some amount of resistance and some amount of conductivity in the parallel path, it is safe to say that in most of these cases P out will be less than P in. Okay. And sometimes instead of taking the linear scale, just the ratio of P out to P in, people also make use of the ratio in decibels. So, they say that one could always take 10 logarithm to the base 10 okay, 10 log to the base 10 P out by P in, and this is the definition of say decibels. Okay. So, with respect to the input power, how much of output power I am getting, this is also measured in terms of decibels. So, since the power is proportional to voltage square, right, you can always write this as 10 log to the base 10, right. So, you can say that this is going to be proportional to the voltage square. If the length of your transmission line is going to be some denoted by Z, alpha is the attenuation constant and the launched voltage is going to be V plus, then you can always write this down as the ratio of output voltage square to the input voltage square. Okay. If this is the case, then the power 2 can be brought outside, and so it will look like 20 times logarithm to the base 10 exponential minus alpha z. Okay. So, if you know the attenuation constant of your transmission line, you can estimate the relative output power in decibels that you will be measuring in your transmission line. So, this is also made use of in practical conditions, right. Output power is expressed in terms of input power in decibels. Okay. And what does this mean? All right, we need to get a feeling for some numbers. Okay. If alpha is equal to 1 nepper per meter and if the length is say 1 meter. Okay. Substituting this, you will get the relative output power to be minus 8.68 dB per meter. Okay. Okay. Since the length is 1 meter, we can write down the relative output power is say minus 8.68 dB per meter. So, if you are having a transmission line of length which is larger than this, then you can always use this as an indicator of what is the net relative output power that you will get with respect to your input. Okay. So, in summary, by including the resistor and the conductor in the transmission line, we are noticing a few effects. The first and foremost thing is that the telegrapher's equations look close to what we had seen before, but have an additional term minus R I in the case of the first telegrapher's equation for the spatial derivative of voltage, and minus G V for the spatial derivative of the current. Now, even though we have written it in a simple form as delta Z tends to 0, while making programmed versions of these, all right, just we have done like we have done in the prior classes, each and every term will matter, all right. So, where you take this voltage, at which instant of time, etc., everything matters. So, small details will cause big changes in your program, all right, and we will be seeing that in the next class. I will not be going into too much details because that is covered in another course at a higher level. However, you still need to have a starting code that actually works. So, we will be noticing that the place where you add or subtract terms in your existing finite difference code will actually make a big difference. We are considering an AC excitation or a sinusoidal excitation. In this particular case, dou V by dou Z can be written as equal to minus R plus j omega L times I, where this I and V are actually written as time harmonic waves, and these are actually exponentials, right. In order to decouple these equations, we can write down the wave equation as dou square V by dou Z square is equal to R plus j omega L times G plus j omega C times V. The procedure for obtaining this is the same as what we have done a couple of times before, all right. All we do is take the derivative of one of the equations and then substitute from the other equation from the telegrapher's equations. So, in order to find out the general solution, we need to make use of this term R plus j omega L times G plus j omega C. If we create a new term now called gamma as square root of R plus j omega L times G plus j omega C, the wave equation will look like dou square V by dou Z square is gamma square V, and this gamma is going to be complex, gamma square is also going to be complex, and gamma is known as a propagation constant. It is a complex number and the unit of that is per meter. Since it is a complex number, it has a real part alpha and an imaginary part beta. The real part is known as attenuation constant, imaginary part is known as phase constant. The unit of alpha is Nepers per meter, unit of beta is radians per meter. Okay. Consequently, the solution for the forward wave will look like V plus e to the minus gamma z, and one can substitute for gamma to be alpha plus j beta. The result will look like V plus e to the minus j beta z, which is the same expression that we had for the lossless transmission line case with the AC excitation, multiplied with e to the minus alpha z. The e to the minus alpha z is going to dictate the amplitude of your voltage wave that is travelling forward. In this case, we are assuming the forward voltage. If alpha is equal to 0, we will say that your transmission line is lossless. That means that it is equivalent to not having the resistor and the conductor in the series and in the parallel paths, which is the case that we had started with. However, if alpha is greater than 0, we call this to be a lossy transmission line, and the interpretation of alpha greater than 0 is as your wave progresses in the z direction near transmission line, the amplitude will decay exponentially. Okay. Now, the other question that normally one would have is what would happen if alpha is less than 0? Alpha less than 0, though mathematically is possible here, it will denote a transmission line with a gain. So, as it propagates in the z direction, it may have higher and higher amplitudes that is also going exponential. However, the physics of the equivalent circuit that we have drawn prevents alpha from becoming negative, okay, because we are using only passive components. If you did want to make alpha less than 0 or provide a gain, you will have to use active components, which is not the case over here. Okay. So, alpha is going to be greater than or equal to 0. The unit of alpha was nepers per meter, and just to understand that, if alpha is going to be equal to 1 nepper per meter, the amplitude of the wave drops to 1 over E over a distance of 1 meter. Okay. This means that we have to define another term that we have not considered before, which means that we have to denote something known as a propagation length, which means that for a given transmission line design, you will communicate with other engineers with an objective term that is called as propagation length. Okay. If your transmission line has R, L, G, C parameters, you will say that the distance over which the amplitude drops to 1 over E its original value is denoted by L, and that is equal to 1 by alpha in meters. Generally, this is the practical length of the transmission line that one could have. But nothing prevents us from making a transmission line longer than this, but the propagation length for objective purposes is 1 over alpha. It still means that you will have a small amount of voltage even after this length, but in the practical scenario, we do not consider the length of the transmission line to be longer than the propagation length, because the value of the signal is going to be too low. Another way of measuring the decay, all right, due to the introduction of resistance and capacitance, is by making use of ratio of the input output to the input power. If the input power is P in watts and the output power is P out in watts, a simple way of finding out the relative output power is 10 log to the base 10 of P out by P in, and this is denoted in units of decibels. Okay. Now, since this is denoted in decibels, right, and this is in power, the power is proportional to the voltage square. So, we can always write this down to be V plus e to the minus alpha z divided by V plus the whole square, and bringing the 2 to the left hand side here. So, it becomes 20 log to the base 10 e to the minus alpha z. So, if you know the propagation constant or the attenuation constant of your line, and if you know the length, you can estimate the relative output power in your transmission line, and if it is going to be very low, then you can actually do something about it or cut the transmission line or make design modifications to reduce R and G, etc. Just to understand this decibels very well, if alpha is 1 nepers per meter and Z is 1 meter, then you have the relative output power to be minus 8.68 dB per meter. Now, there is one additional detail that you will have to notice, that is, there is a negative sign. The negative sign here denotes that your output power is less than your input power. Okay. If your output power is equal to the input power, then your relative output power, this measured in decibels, will be 0 dB. Okay. If you get a positive sign for this equivalent circuit, that means that something is wrong. All right. If you have a positive sign at the relative output power in decibels, it means that your power at the output is actually increased compared to the input. So, there are some small details that you will have to keep in mind when you are drawing an equivalent circuit with all passive elements. You should end up with a negative relative output power in decibels. Okay. So, this concludes this lecture.